All right, so counting is really important in probability, and there are several counting rules that we need to look at. In order for us to calculate probabilities, we can almost always try to go back to the basic formula or our classic formula for probability. The probability of an event E is equal to the number of outcomes with E divided by what? Total number of outcomes. Very good. So, with a lot of the problems that we've looked at with multiplication rule and things like that, it's possible that we could have solved them in a different way if we look at some of these counting rules. Okay, and so we'll look at being able to count things like the number of outcomes with E and the total number of outcomes, and then how we can also use that to calculate probability. Okay, so about 5 rules we're going to look at. The first one is called the fundamental counting rule. It says the number of ways that 2 events can occur together if the first event can occur m ways and the second event can occur in n ways is m times n ways. And that can be extended to any number of events. Okay, so it says a social security number consists of 9 digits in a particular order, and repetition of digits is allowed. If randomly selecting digits for one social security number, what is the probability you get the social security number of the president? Okay, so 2 things. Sometimes the problems in this section will ask us how many, and sometimes they'll ask us, like we see here, what is the probability? Okay, and we'll have to go one step further to get this probability. But if we're interested in the probability of randomly generating the social security number of the president, and we use the formula that we just put up top there, how many outcomes would result in the president's social security number? 1. Okay, that part we already got, and on the bottom we need to figure out the total number of outcomes. Okay, so I suggest that the fundamental counting rule can let us do that. They just told us that there are 9 digits in a social number. Okay, and so when we talk about events, these aren't major things. They're not parties or whatever. It's just something that we have to make a choice about. And so I can make a choice about the first digit. How many ways could I fill that first spot? One more. 10. There are 10 digits. Okay, and here it mentions that we can do what with the digits? Repeat. Okay, so for the second spot there are 10, and the third, and for every spot we have a choice of 10 digits, and so that's going to give us 1 over okay, 1 billion different did I do enough? I think I did. Okay, 1 billion different social security numbers that we could generate. Okay, questions about that? There's more social security numbers? There can't be, unless we come up with a different scheme, unless we didn't multiply right. Maybe that could be possible. 10 to the 9th is okay. I am considering I don't know what the population of the United States is, but oh, well then we're good for a while. All right, questions about that? Okay. All right, very good. Okay, let's look at another one. The rules are pretty simple. It's just really a matter of knowing when you're going to use that rule. In the game of blackjack played with one deck, a player is initially dealt 2 different cards from the 52 different cards in the deck. Find the probability of getting a 2-card initial hand consisting of the ace of clubs and the ace of spades, I think that should say, in any order. Okay, ace of clubs, ace of spades. Okay, so pretty much, well, how many ways, since they say any order, I got to think about that. How many ways could we get the ace of clubs, ace of spades? Since it says in any order, if we use our fundamental counting rule, for the first spot we've got how many choices? 2. It could be either one, and then for the second there's just 1. So there'd be 2 different outcomes. That's breaking it down into those simple events. Remember us talking about that in our sample space? And especially since they mention in any order, we're going to count every order that it could possibly happen. Then on the bottom, we need to know how many ways we could get any 2 cards. And that would be what? One out of 52? So if we're using fundamental counting rule, we're going to say what? 52 times 51. That's going to be our denominator. Okay, so 52 times 51. Very good. So we get 2 over 2,652, or what? 1 over 1,326. Okay. Questions about that? Okay, very good. Fundamental counting rule is very powerful and important. A lot of the other things that we're going to look at are special cases of the fundamental counting rule. One thing about counting is a lot of times you can get the answer in more than one way, and if you can get the answer in more than one way, then chances are it's probably the right answer. Let me just hit a couple of classic examples that I didn't include on the handout. License plates. In South Carolina, I won't tell y'all the long story about license plates. I think I included that in the recording the other day. But I've been watching the Sunrise license plates, and they've been distributed in alphabetical order. Yeah, we'll just leave that at that. But anyway, once I recognized that, it became a math problem for me. I wanted to know how many different license plates would we be able to generate if we use 3 digits and 3 numbers. Okay, and it does look like the digits and numbers can both be repeated. Okay, so using fundamental counting rule, how would I figure this out? Okay, we got 26 letters in the alphabet times 26. Okay, times 10 times 10 times 10. And that comes up to whatever. Very good. 576,000. Okay, excellent. Okay, so that's how many license plates we could generate using that scheme. And I thought we wouldn't get past a certain point, but we've already gone past that point. I think it's down to J's now. But anyway, we won't talk anymore about that. What about area codes? Many years, the area code in South Carolina, the only one, was 803. Okay, area codes had much stricter rules than they do now. Area codes could not begin with 00, or they couldn't begin with a 0 or 1. Could not begin with 0 or 1. Okay, they cannot end in 00 or 11. Those were reserved for special numbers and emergencies. And the middle digit, second digit, could only be a 0 or a 1. Old rules. Okay, so with these rules, how many different area codes could we have in South Carolina? Not many. Well, not South Carolina. It was the entire country. So could not begin with 0, 0, or 1, 1. So for the first spot, how many choices do we have? 8. There were only 8 choices. For the second, how many choices? 2. It had to be 0 or 1. There was no 864 or 863 or some of the crazy things you see now. And then it could not end in 0, 0 or 1, 1. Think carefully on this one. Not 8. Not 10. Not 2. 9. Okay? You could choose a 1 for the second spot, but then that was the only thing not eligible for the last. 0 would be okay. Right. So once you decided what this middle one was, we still had 9 choices available. And so when you do that, question about that? When you do that, that came up to 144 different area codes, which is a little less than 3 per state. And now that we have pagers, well, I don't know if anybody has a pager anymore, cell phones and all these different things, fax machines, we needed more numbers. And so we had to go away from these rules. Okay, was there one more that I want to talk about that's kind of classic? Well, that's it for now. Okay, so fundamental counting rule. Pretty simple rule, but very, very, very powerful. All right, the second rule is called the factorial rule. It says the number of different permutations. When we talk about permutations, we mean the number of ways we can arrange objects. Okay, the arrangement of the object matters. When we talk about permutations, ABC is different from BCA, which is different from CBA, ACB, BAC, and CAB. 6 different permutations for those 3 objects. Okay? And in fact, we'll use our rule in just a second to show us that that's what we should have gotten. But the number of different permutations of n items when all of them are selected is n factorial. If I want to know how many ways I can arrange n objects, then it's n factorial. What is n factorial? N factorial is 1 times 2 times up to whatever n is. N has to be an integer. I didn't need that exclamation mark at the end. Okay? It's the product of the first n integers. Okay? So instead of writing all of that out, we just call it n factorial. Okay? So for our little example here on the side, I've got 3 objects. I want to know how many different ways I could arrange all 3 of those objects. It would be 3 factorial, okay, which is 1 times 2 times 3 or 6. Okay. Same thing as what? What other rule could we have used to get this answer? We only talked about one other one today. Fundamental counting rule. For the first spot, we would have 3 choices. The second 2, the last 1. Okay, so that's the second way that we could get that answer. Very quickly, on our calculators, if I want to get 3 factorial, I'm going to hit 3. Going to go over to math. And PRB is the probability menu. Number 4 has that factorial symbol. And so we don't have to type all of that in. It'll do it for us. We get 6. Okay. All right, so here we are. We're hosting a dinner party for 8 people. In preparing the seating arrangements, you would like to know the number of different ways in which the guests could be arranged. All right, so I've got 8 people here, and I'm interested in arranging all 8 of them. All right, that meets kind of the conditions of the factorial rule. If I've got n objects and I want to know how many ways I can arrange all n of them at a time, that's factorial rule. And so the answer here would just simply be 8 factorial. Okay, 40,000 something, I think. Very good. Okay, 40,320. 40,320 different ways. Okay, so if you've got everything else out of the way and you're just the party to start, you can sit down and think about the 40,000 ways you could arrange the people. Okay? All right. Here we have a FedEx driver. He has time to make deliveries at 3 locations among the 8 locations remaining. How many different routes are possible? Does this meet the criteria of factorial? Does it? No, why not? Well, in this case, we're asking how many different routes. So the order, that's what he's interested in. The route would consider the order in which you're going. What's key about factorial rule? Of the n objects, how many of them do we want to arrange? All of them. Okay. In this problem, we've got 8 objects, and he's only arranging how many? 3. Okay. So this doesn't meet the criteria of the factorial rule. Looks like it may have gotten a little misplaced. So let's see what the next rule is. Looks like it got a lot misplaced. Here is a permutation rule, and it says the number of arrangements when n different items are available but only r are selected is NPR. Okay, NPR is a function that's on your calculator. We could write out the formula for permutations. NPR equals n factorial over n minus r factorial. Okay, how? That's already built into your calculator. So what you need to think is NPR, where n is the number of objects available and r is the number that we're choosing at a time. So if you're having that dinner party and you've invited 8 people but you only have 5 chairs, okay, we can't do factorial here. We're not using all of the people. Okay, we can only choose to let 5 of them sit down at a time. So we would do a permutation, okay? And since we're talking about seating arrangements, the order does matter. So we would just say 8P5, or on our calculator, we're going to go 8, go over to math, PRB, and you see number 2 is NPR. And we're choosing 5. And so we get 6,720 different ways we could choose 5 people to sit down at a time. Come on. Okay, questions about that? All right, let's back it up then to those other examples. Okay, with the short time remaining, the FedEx driver has time to make deliveries at 3 locations among the 8. How many different routes are possible? Okay, so we would say what? 8P3. Okay, what does it come up to? 336 different routes. Okay. All right, an author currently has 7 different books in print. If those 7 books are stacked in a random order, what is the probability that they are arranged in alphabetical order? Okay. So this problem is a probability problem. So if we're looking at probability of alphabetical order, we need to consider how many different orders are alphabetical, how many? How many? How many ways can you arrange the books in alphabetical order? One. There's only one way to arrange the books in alphabetical order. And then how many ways could we arrange these books all together? Okay, we could do 7 factorial. We've got 7 objects, and we're arranging all 7 of them at a time. You could also do permutation. If you do 7p7, that's the same thing as doing 7 factorial. Okay, so either one of those. All right, so we get 1 over 5,040. Okay, 1 over 5,040. Questions about that? Okay, very good. All right, did we get all of those? Okay, what about this next one? The board of directors of a local college has 12 members. 3 officers, president, vice president, and treasurer, must be elected from the members. How many different possible slates of officers are there? Okay, so how do we approach this problem in our thinking? First of all, I note that the problem is asking me what? How many? Okay, it's a counting problem. All right, then I'm going to kind of look at the information and figure out which of the rules I have. I think a big clue is when you have so many objects available and you're choosing a subset. All right, that kind of narrows it down for me. I'm not going to use factorial. I'm not really going to use fundamental counting. It could be permutation or another rule that we'll talk about in a minute. Okay, but when I look at this, I've got what? How many objects available? 12. And how many spots do I need to fill? 3, right? 3 officers. Okay, so the question is, between this rule and the combination rule, which we'll talk about in a few minutes, does the order matter? Does the order matter? Okay, so I'm not going to call any names in particular right now, as everybody's doing a pretty poor job. But okay, so for president, vice president, treasurer, we'll just do some old names. Let's say we have Ford, Nixon, and I don't know, McCarthy or something. Okay, is that the same as if I said, no, we're going to have Nixon for president and Ford for vice president, and then McCarthy can still be treasurer? Do we regard these two things as the same? No, because the order matters, right? Why? Because in this case, we've got specific slots. Okay, so if we have specific slots that have to be filled, you know, this is the president slot. This is the vice president slot. So if I rearrange the names, then that's a different configurement. It's a different arrangement. The order really does matter. And so we would say 12p3, which comes 1,320. Very good. All right, questions about that? Okay, very good. Okay, here's another rule. This is one where we have permutations where some items are identical to others. Okay, if we've got items repeated, then if we rearrange some of those things, you can't really tell the difference. For instance, we're going to look at this word statistics, and if I say, okay, I want to have statistics, okay, and then I say, no, instead of that, I think I want to have statistics. Can you tell a difference? I mean, you saw me do that. But when you count, I mean, it's the same thing, right? And so when we have some items that are repeated, there's really no need to count every configurement because some of them actually come out to be the same. So the formula for this is a little complicated. It looks like this. First of all, we're going to do n factorial. That's going to be in our numerator. And this one's not built into your calculator. On the bottom, we're going to look at all the different types of objects. For instance, I've got, so many S, so many T's, so many A's, so many I's. So I'm going to say N1 factorial times N2 factorial times ... NK factorial, where I have K different types of items, and then N1 plus N2 plus NK ... NK should equal N. They add up to the total. Okay? So, if I want to know how many different ways that the letters of statistics can be arranged, first thing I need to do is figure out how many letter S I have. 3 of those. I've got 3 T's, 1 A, 2 I's, and 1 C. Okay, so when we count those, it's going to be how many letters altogether? I counted 10. So it's 10 factorial over 2 factorial, 3 factorial, 3 factorial, 1 factorial, if you want to be technical, and 1 factorial. 1 factorial is just what? 1, so don't spend a lot of time keying that in. 2 factorial is just what? 2. 1 times 2 is 2, so don't spend a lot of time keying that in. And the rest of it you can really, except for maybe the 10, you could do in your head. 3 factorial is 6, so 36 times 2 is 72. So 10 factorial divided by 72. Okay, 50,400. Okay, did everyone get that answer? All right, so this is a permutation with repetition, you might call it, because some of the items are actually repeated. Okay, permutations with repetition. Okay. All right, the last rule is the combination rule. It's very similar to the permutation rule, except order does not matter. Okay, when we listed all of those A, B, C's earlier, and we came up with 6 different permutations, that would just be one combination, because how you list it doesn't matter with the combination. So it says the number of different combinations where order does not count when n different items are available, but only R of them are selected without replacement is NCR. You probably saw that on your calculator already. Note that arrangements of the same items are counted as being the same. In essence, order does not matter. Okay, so for instance, a pizza shop offers a combination pizza consisting of a choice of any 3 of the 4 ingredients: pepperoni, mushrooms, sausage, and anchovies. Determine the number of possible combination pizzas. Okay, so I look at this, and kind of key to me, first of all, is I'm determining a number, not a probability. Okay. But I've got 4 objects available, and I'm choosing how many? 3. Okay, so that kind of narrows it down for me to either permutation or combination. I'm going to ask myself, does the order matter? No, it doesn't. Unless you're OCD, the order does not matter, right? Okay, y'all, some of y'all are still questioning that, but all right, so in that case, I would do a combination, not a permutation. Okay, so 4, choose 3, and on the calculator, I would do 4, math, PRB. Going to select number 3, and we're choosing 3. And so we come up with 4. Okay. Questions about that? So none of the formulas are really, complex, especially since we have our calculators. The key is to figure out when to use each formula. Okay. So let's look at a few more examples. Some of these are just counting. I think some include probability. Randomly graded homework problems. A professor grades homework by randomly choosing 5 out of 12 homework problems to grade. How many different groups of problems can he possibly grade? All right, so what do you see in this problem that might help us figure out how to solve it? Say it again. I just didn't hear it. Are we counting or are we calculating probability? Counting. It says how many. Okay. All right, what else do we see? Okay, not choosing all of them. We've got 12 of them and choosing only 5 at a time. So it could be a combination. It could be a permutation. Does the order matter? No. Okay, if the professor decides, I'm going to choose problems 1, 2, 3, 4, and 5, and then he turns around and says, no, I think I'll choose 5, 4, 3, 2, and 1, it's the same problems, right? If you didn't do those problems, you get the same trouble. It doesn't matter about the order in which he selects them. So that would be a combination. We would say 12, choose 5, which is what? 792. Okay, 792 different ways in which he could choose problems. All right, questions about that? 5 problems from the 12. Okay, let's look at this next one. A clinical test on humans of a new drug is normally done in 3 phases. Phase 1 is conducted with a relatively small number of healthy volunteers. For example, a phase 1 test of bexarotene, I have no idea what that is, involved only 14 subjects. Assume that we want to treat 14 healthy humans with this new drug, and we have 16 suitable volunteers available. Okay, if the subjects are treated, or rather are selected and treated in sequence, so that the trial is discontinued if anyone displays adverse effects, how many different sequential arrangements are possible if 14 people are selected from the 16 that are available? That was a lot, but this was a problem that was from your textbook. So I wanted to make sure I included some that had all of the author's style. Okay, so what are we going to do here? Big clue every time is going to be if I've got so many objects and I'm choosing a subset. Do we have that here? Yes, we got 16 available. We're choosing 14. So the only question I need to ask is, does the order matter? Yes. Okay, they're taking their time. They're not just throwing the treatments out there and everybody goes. It looks to me like they're giving a treatment to a person, waiting a period of time before they give it to the next. Because if they see some adverse effects, they stop the treatment altogether. So in this case, I would say 16 P 14, which still comes out to be a large number, as I recall. Okay. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay. Factorials grow very quickly. On your calculator, you're not going to be able to calculate more than about, I think, 69 factorial. After that, your calculator is going to give you an error. Okay. But that's how many different ways they could do it. If we have 16 and we're choosing 14 at a time. And the order matters since they're doing this sequentially. Okay? All right, if 14 subjects are selected from the 16 that are available and the 14 selected subjects are all treated at the same time, how many different treatment groups are possible? Okay, 14 are selected. We're treating all from the 16. All of them are treated at the same time. So that tells us what about this problem? The order doesn't matter. Okay, we're still choosing 14 from 16. So this time we're going to do a combination. Okay, 16, choose 14. Combinations will always be less than permutations. Okay, what'd you get? 120? That's a lot less. Okay. All right. Questions about that? Okay, very good. All right, part C. If 14 subjects are randomly selected and treated at the same time, what is the probability of selecting the 14 youngest subjects? Okay, how would we calculate that probability? Okay, we can always go back to our classic formula for probability. Okay, so that would say we're going to look at the number of ways in which we could select the 14 youngest. How many ways can we do that? One, right? There's just going to be one way in which we select the 14 youngest. And then altogether, how many ways can we select 14 where the order doesn't matter? 120. Okay, 1 over 120. Questions about that? Okay, very good. All right, sometimes we can combine some of our rules. Is this the last problem? Oh, okay. Before we do this one, what about 5-card poker hands? That's another interesting one. How many different 5-card poker hands can we make? Anybody want to take a guess before we calculate? A lot, okay. All right. Well, what do we need to consider here? Okay, how many are in the deck? There are 52 cards in a deck. Okay, the other issue is what? Does the order matter? No, how you hold the cards in your hand, that doesn't make it a different hand. So the order doesn't matter. So what do you think we're going to do? We're going to do combinations. 5. 52 C5, which comes to be about 2.6 million. Okay, 2,598,960 different 5-card poker hands. Okay, that's a lot. Alrighty. Questions about that? Okay, back to that last problem. It says a food manufacturer is analyzing a sample of 400 corn kernels for the presence of a toxin. In this sample, 3 kernels have dangerously high levels of the toxin. if 4 kernels are randomly selected from the sample, what is the probability that exactly 1 kernel contains a dangerously high level of the toxin? Okay. Okay, so we're interested in the probability of getting 1 of 4 with toxin. Okay, and if I go back and think about my classic formula for probability up top, I need to know what? That have what? How many toxins? Or how? 1. Okay, so the number of ways to get exactly one with toxin. And on the bottom, we're going to have what? Not just the number of kernels. What do we have to do in this case? We got to select 4, right? So we want to know the number of ways to get any 4. Okay, up top, we want to get 4 where only 1 has toxin. And on the bottom, it's any 4. Okay? All right, the experiment here is selecting 4 kernels. So on the bottom, we're looking at all the ways we could select 4. And again, up top, we're looking at ways to select 4 where only 1 is toxic. Okay, so how could we do that up top? Well, let's do the bottom first because that's usually easier. How many ways can we select any 4? What is it? 400 C4. Very good. Okay, 400 kernels available, and we're choosing 4 of those at a time. Now at top, it's going to be a little bit tricky because in order for us to get exactly 1 that has the toxin, then we also have to have what? If we're selecting 4, the other 3 must be what? Without 3 good kernels. Okay? This piece up top kind of brings us back to fundamental counting. All right? We're looking at the number of ways we can choose exactly 1 that has the toxin, and then we're going to multiply that by the number of ways we can get 3 without the toxin. Okay, so 1 with the toxin, to get that I'm going to say 4, choose 1, because we have 4 kernels that have the toxin, and I only want to choose 1 at a time. Is that right? Or is it 3? 3 kernels. Okay, so 3, choose 1. Okay. 3, choose 1, which is just 3. Okay, but then how many good kernels do I have left? 397. And how many do I need to choose? 3. So that 1 plus 3, that adds up to the 4 that I need. I've got 1 good one, and rather 1 toxic one and 3 good ones. And so do all that in your calculator and I'll give you the answer. Okay. I got 0.02955. Okay. Questions about that? All right. Do you think there's a different way that we could have gotten that probability? Yes, no, maybe? Probably. Okay. All right, good. All right, well, you think about it and see if you can come up with it a different way. Okay? But that pretty much covers what will be on the test. I encourage you to take a look at the practice test.